So I'm going to tell you all about exoplanets and the search for life, specifically around low-mass stars, but in general, just the search for life and what we're doing, what the future holds. So the first question you might ask is, how many exoplanets do we know about? It's a lot. It's a lot of exoplanets. So this is showing you the exoplanet discoveries over time. The first exoplanet was discovered in 1995. That was a very big exoplanet. That was a Jupiter-sized exoplanet. And while that's fun and interesting, Jupiter, as we know it, doesn't have any life. So we're not that interested in finding more Jupiters. What we would really like to find is something Earth-like, a terrestrial planet. So there's a few discoveries here after 95. We had a technique to find them, and then we're like, well, let's apply this technique, and let's see how many planets we can find. And then all of a sudden, you hit 2014, boom, this huge jump in exoplanets. And then recently in 2016, you had another big jump. And it's due to this thing called Kepler, which I'll talk about a little bit. Kepler is a space telescope. Now, not all of these planets are validated, are confirmed planets. As you can see, some of these are discoveries and some of these are newly validated. But before a planet is validated, it's a candidate planet. It's something we think is a planet, and then it has to go through an extra process to be validated, and I'll talk about what that is. I checked yesterday, and I think the current count was 2,950 validated exoplanets. So those are exoplanets that we know for certain. Almost 3,000 exoplanets. And if you add in all of the candidate exoplanets, it's like 5,200 something. So there's a lot of planets that we know about. And I talked about an Earth-like planet. This is the Kepler Space Telescope. Its mission was to find an Earth-like planet around a Sun-like star. The reason we like those is because that's where we live. That's the best chance for life that we know of. So Kepler was designed with this one mission to stare at this little patch of sky right here. And originally it was designed for a 3-year mission. And I'll tell you exactly why that is in a couple of slides. But each one of these little boxes, these are basically CCD cameras. And one of these little boxes is roughly the size of the moon. So you can see that it had a relatively big field of view. And all it did was stare at this one patch of sky that's right over the plane of the Milky Way. Now, why did it decide to look here and not anywhere else? Well, it was decided that this part of space had the most sun-like stars in it. And not only that, but sun-like stars that had the most similar characteristics to what we think our sun has. So stars that were about the same mass, about the same age. It's your best bet to find something that looks a lot like the Earth. So it stared here for 3 years to look for an Earth-like planet. And what exactly do I mean by Earth-like planet? A lot of times we talk about habitable planets or the habitable zone. Basically what that means is we're looking for a planet that can support liquid water. We think liquid water is essential for life. So this plot here is showing you where this habitable zone is as a function of stars of different masses. So these are big stars, and these are small stars. And right here at 1, this would be a sun-like star, a star just like our sun. And then you have the distance of the orbit from the star. So you can see that Earth is right at this 1, 1 mark right here. All the planets of our solar system are right here. But this is where Earth-like planets would exist, in this blue band. So all of these little squares are planets that we've detected. And there's a few things in there, as you can see. There's not a whole bunch. We'd like to get a lot more of that because of statistics. But you can see that Earth is right inside there. And Mars is actually just like right on the outer boundary of there. So Mars may have had habitable conditions, may still potentially be good for habitable conditions. I'll let Elon Musk figure that one out. But we're very interested in planets that we can find here. If you're too close to your star, It's too hot. It's too dry. You get something like Venus. You get something like Mercury. Water cannot exist. It boils off. And if you're too far away, then it all turns to ice. And that's no good either, because you can't swim in ice. It's not part of the primordial goop that we all came from. We're going to talk more about these stars at the bottom. But what's important to note is this is a log scale here. So the habitable zone for this really small star here, it's 0.2 times the mass of the sun. This is 10 times closer than it would be here. 10 times. It's much smaller. So how do we find exoplanets? There's actually a lot of different techniques that we use to find exoplanets. I'm going to talk about a couple of them. And if there's time at the end, I can talk about some of the more exotic ways that aren't used quite as frequently but are very interesting. I'm going to start roughly in order of the number of planets found by the technique. So this is the transit method. This is what Kepler used when it was observing that one field. Let me see if I can click on this to get it running. OK, I'm going to play this a few times, just so you know. So the idea is we're out here, and we're looking straight at this star. And what we observe is how much light this star is producing while we're watching it. So you might have missed that. I'll play it again. You can see that we see just a steady amount of light. Stars may twinkle in the sky, but once you remove the sky, they don't twinkle too much. OK, so you can see that as you're viewing this star, and you're seeing how much light comes from it, once this planet passes in front of it, you get a dip. It basically blocks out some amount of light. Seems like a very straightforward way to detect a planet. You want more than one dip. One dip could be statistical error. 2 dips could be slightly less statistical error. 3 dips is nice. That's like a 3 sigma event. You have 99% chance, 95% chance that that could be right. So the reason that Kepler's original mission was for 3 years is because if you're looking for an Earth-like planet around a sun-like star, it takes 3 years to get 3 transits. You have to look at one star for 3 years in order to see 3 dips, if it's like Earth, if it's just as far away from its star. Now, this technique is very dependent upon the size of the planet orbiting the star. Basically, it depends on the size of the planet and the size of the star. If you take a star of the same size and you put a bigger planet around it, like this one, you get a much bigger dip. And if you put a smaller planet around it, you get a much smaller dip. I'll play it one more time, because why not? Conversely, if I had a small planet around a big star and a small planet around a small star, it would be much easier to detect that small planet around a small star. OK. And what if you have more than one planet? What if you have a whole system of planets that are orbiting your star and transiting? You might see a light curve kind of like this one. So you see lots of dips, and you see dips within dips. And we see this. We actually see this. OK. So let's talk about one of those stars. This is the discovery paper of the most Tatooine-like planet ever discovered. For those of you that are not Star Wars fans, Tatooine is a planet that orbits 2 stars. That was great in science fiction. Problem is that physicists said that couldn't happen. It was an unstable system. You couldn't find a planet around 2 stars. And then we found a planet around 2 stars. I'll point out the features here. This is actual data from Kepler. So this is basically time going this way. And these are the dips that you would see. So blue is when star B eclipses star A. So star A is the big star, and star B is the smaller star, and then you have planet B. Planets always start at B. There's no planet A. A is reserved for the star. So this has one planet around it, and the planet orbits outside of both the stars. You basically have the two stars orbiting each other, and then you have the planet outside of that, orbiting both of them. So when star B eclipses star A, you get this huge dip. And that's because star A has most of the light. So now you're blocking out the star that has most of the light. And when star A occults star B, you get a smaller dip, this yellow dip. And then when the planet transits in front of star A, you get these green dips. And you can see that they are periodic, and they happen roughly at exactly the same time difference. That's how planets work. And then you get these tiny, tiny little red dips that are very hard to see. But that's when planet B transits star B. I think we found maybe 3 systems like this, 2 or 3 systems like this. Not a lot, but enough to say that they exist out there, and not quite as rare as we originally thought. To reiterate about this method, the sensitivity with which you find a planet, for this method, it depends both on the radius of the star and the planet. If you take a small planet, we'll say an Earth-like planet, and you put it around a big star and a small star, it only makes a small dip when you put it transiting in front of the big star. But when you have it transiting in front of a small star, you get a much larger dip. So it's actually easier to find Earth-like planets around a small star using this method. That is fantastic. Except Kepler did not look at a lot of small stars. I'll talk about another method that we use. This is one of the ways that we validate a planet. So typically, when Kepler sees a planet, that's a candidate. Then we need to go and look at that planet with a completely different method. There's 1 or 2 caveats to that, but in general, that's true. And this is usually the method that we use to follow up on that planet, to see if it's actually real. It's totally independent of transits. It's called measuring radial velocities. Sometimes it's called Doppler spectroscopy. Basically, a planet and a star orbit around a center of mass. A lot of times we think about the planet orbiting around the star, but that's not technically true. There's a center of mass. You can think of this as like a lever that has a big weight on one side and a small weight on the other. And where you put that pivot so that it balances out is not necessarily right on the big weight. It's somewhere between the big and the small weight. Same thing with a star and a planet. You have a center of mass, which in this case is right here. So you can think of this as the planet giving a little tug to the star. That does something very interesting with light. When the star is moving away from us as we're viewing it, the light gets red shifted. It goes to redder wavelengths. And then when it's moving closer to us, it gets blue shifted. And we can measure this shift in the light. And we measure this shift over the time of the orbit, because we have an estimate of the orbit if we have the transit signal of it. We know it's going to orbit once every year, once every half year, whatever. So we can make our observations, and we can look at that. I will play it one more time just so we can appreciate it, because this is a much harder measurement to make, to get a spectrum of the object, to notice if it's red or blue shifted. It's much easier to do the transit method, which is why like 95% of the planets that we know about were found with the transit method, because I can basically just stare at a big patch of the sky and look at all the stars and just see how they dim over time. It's not just done from space. We do it from the ground. There's actually a ton of projects that are monitoring stars for planets all the time from the ground. And once again, we can talk about what the different size of star will do to the orbit. So if you have a small planet around a big star, the center of mass is very close to the center. So this planet actually tugs on this star just very little. It doesn't do that blue shift, red shift too much. But if you decrease the mass of the star, you get a much bigger tug. So once again, it's easier to find small planets around small stars than it is big stars. Why aren't we looking at all the small stars? Well, we're getting there. We're starting. Let's talk a little bit about low-mass stars in general, because there's some other interesting characteristics about them that I think are worth knowing. So here you have the sun. You have a low-mass star, a brown dwarf, which is basically a failed star. There's some mass in between these two objects at which it becomes a brown dwarf versus a low-mass star. And then you have Jupiter, which is kind of similar to a brown dwarf, and you have Earth. You can see that the low-mass star is probably closer in characteristics to this brown dwarf, at least in size and mass, than it is the sun. The sun is much bigger than a low-mass star. These stars have less than 60% the mass of the sun. So they're also roughly half the size of the sun. And they're called cool stars. Sometimes we call them ultra-cool stars. They have temperatures less than 4,600 Kelvin, which, if you haven't done physics and you're not acquainted with Kelvin or Celsius, the sun is about 5,800 Kelvin. So this is less than 1,000 Kelvin cooler than the sun. And they also go by red dwarfs or M dwarfs. These are how we like to term them in a popular writing. M dwarfs is the scientific name for them, but red dwarfs is kind of nice too. Okay. Another interesting fact about low-mass stars is they're everywhere. This is a 10 parsec sample. If you're not familiar with the parsec, which maybe you didn't watch Star Wars again, but this is roughly 33 light years, 10 parsecs. So basically the distance that it takes light to travel in 33 years. So if I just made a big sphere of 33 parsecs, and I counted, or 33 light years, and I counted all of the stars within that volume, this is what I'd find. We broke them down by, we call this spectral type, but you can think of it as mass, size. So these big guys, these A stars, there's 4 of them. There's 4 of them in that volume. There's not a whole lot. And then you move out, you get to G-type stars. This is what our sun is. So in the solar neighborhood, there are 20 stars like our sun, roughly. And then there's slightly more stars that are lower than that. And then you get to the M dwarfs, and you have hundreds now. You have hundreds of M dwarfs just within this local volume. There are tons and tons of these small stars. And then if you go to even lower objects, you have far fewer. So it peaks at here. This is where all of the mass of the universe goes into, is these small stars. They make up 70% of all of the stars in the galaxy, roughly. Another interesting fact about them is they have less than 10% the luminosity or brightness of the sun. So even though there are so many of them in our local galaxy, if you go out to, I don't know, Anza Borrego, wherever you go to stargaze, on the darkest night, and you look at all the stars out in the sky, none of them are these little red dwarfs, these little M dwarfs. You can't see them. They're just too faint. Very, very faint. Another very interesting discovery in recent years is that half of these systems contain 5 or more co-planar planets. You can just think of this as half of these systems contain 5 planets, which means that roughly every single one of these stars has 2.5 planets. And not only that, but due to the fact that the habitable zone is so close to these low-mass stars, you actually are basically only making terrestrial planets. You're not making Jupiters around these stars. You're making only Earth and Mars type things. That's great. So we're basically saying all of these systems have 2.5 planets that could be somewhat like Earth. Those are pretty good statistics when you add in exactly how many stars there are. Another very interesting fact is that they have very long hydrogen-burning lifetimes. Hydrogen-burning lifetimes is what we care about. That's what we call a main sequence star. Our sun right now is on the main sequence. It's burning hydrogen. When it leaves the main sequence, it'll turn to a red giant and we'll all be dead. It won't matter. So we don't care about that part. We care about them when they're on the main sequence. So what I'm showing you here, this is mass of the star relative to the sun. So the sun would be right here at 1. I guess it's right here. It's not this line. It's like a little bit to the right of this line. But this is mass of the star and then how long it lives on the main sequence in billions of years. So you can see these supermassive stars, they don't live very long. This is a log scale. This is 1 billion years. This is 100 million years. This is 10 million years, right? So our sun is roughly 4.5 billion years old. So it's like right here, somewhere around here. Current age of the universe is this line, 13.7 billion years. None of these stars live that long. But low mass stars are all found up here. So what that means is that if a low mass star was created at the very beginning of the universe, it is still burning hydrogen today. It's very efficient. That's great. That means that a civilization that came up on a low mass star could just survive much longer than we have, double the time. They live forever. They're very small. They're very faint. There's lots of them. They also have these planets that orbit very close in. So this is one of the objects that was discovered by Kepler, KOI 961, Kepler Object of Interest. I think this has changed since then because now we've verified it. But this has 3 planets. And here, it's being compared to Jupiter and its 4 largest moons. And this is roughly to scale. And you can see that these 2 systems, they look kind of similar, both in sizes and relative distance of the orbits. Much more similar than if I was to compare this system to our own solar system. So you have all of these planets orbiting these stars. They're very close in. This one has been hitting the news a lot. And one of our local astronomers at UC San Diego, Adam Burgasser, was on the discovery paper of this system. It's TRAPPIST-1. This is the lowest mass star that we found with a planetary system. And we didn't just find 1 planet around this system. We found 7. 7 planets around this 1 star. This is interesting because people have not focused on these very, very lowest mass stars. But after this discovery, I can guarantee you that now people are turning a lot of telescopic resources and looking at these types of stars. And you can see that this entire system, the star and all of the planets, fit within the orbit of Mercury. And very, very far within the orbit of Mercury. So these are very, very tightly packed systems. And here, once again, we're showing the habitable zone. So these planets are probably too close in. It's probably too dry. Not necessarily Earth-bearing planets. D is like right on the border. But you have E, F, and G, which are roughly in the habitable zone. So you have one star with 3 potentially habitable planets around it. And that's just a single star. Who knows what we'll see when we start looking at a lot more of these stars. This star is also roughly twice the age of our own sun. So this is the estimate. The error bar is fairly large. I've argued with him over that. But science is science. You know, as long as you report your errors, it's fine. This is giga-years, but in normal speak, that's billions of years. So 7.6 billion years, and our sun is roughly 4.5 billion years. So this is almost twice as old as our sun, which makes it interesting. You know, if there's civilization on these planets, it's twice as old potentially as we are. But what have they discovered? Have they destroyed themselves? If they destroyed themselves, we're not going to find them, so it doesn't matter. But this will be one of the targets that we definitely look at with the next generation of instruments to actually look for life. We haven't quite gotten to that conversation yet, but we're working up there. So we can run the numbers. Some people are pessimistic about this. But if there's roughly 300 billion M-dwarfs in the galaxy, and there's 2.5 planets per M-dwarf, and you know, many of those are in the habitable zone, not all of them, but many of them, it's roughly 750 billion potentially Earth-like planets. 750 billion. And now if somebody asked you if 1 in 750 billion had life in it, you might say, that's not terrible odds. It'd be a shame if all of them were just barren worlds. And that's only the low-mass stars. We haven't talked about sun-like stars, which we also know have planets, just like our own solar system. And then there's stars in between our star and M-dwarfs, too. So you can add in a lot of numbers there. So we can talk about what the future holds. Some of you are familiar with the Hubble Space Telescope. It's basically the workhorse of astronomy. And then there was an infrared mission called Spitzer. And then there's Kepler, which we talked about. Kepler originally had a 3-year mission. But it was so good at what it did that they kept on asking NASA for more time. And NASA said, sure, we'll keep giving you more time. So it ran for another year, and then it broke. It broke twice. And once it broke twice, it couldn't do its mission anymore. Its mission was originally to just stare at that one patch of sky, but it needs stabilizers. It needs stabilizers for each axis, right? So we live in a 3-dimensional world. You have to keep it stationary in 3 dimensions. It had four reaction wheels. One was like extra in case something broke, but then that one broke, and then the next one broke. It wasn't good, but somebody came up with a very interesting solution. Kepler has this solar shield, and it's shaped kind of like this. So they realized if you tilt it towards the sun is constantly blowing off a solar wind. So this solar wind will actually balance that one extra dimension, and then you can use the reaction wheels to keep it steady in the other 2 dimensions. So they designed a new mission called K2. It's slightly different because it can't just stare at one patch of the sky forever. It has to stare at one patch of the sky for 80 days and then move on. But through that mission, we've already found probably more planets than the original mission found, because now we're looking at lots of different types of stars. The successor to Kepler is going to be this thing called TESS, the Transiting Exoplanet Survey Satellite. Now this satellite is slightly different than Kepler. Kepler was just interested in looking at this one field for an Earth-like planet around a Sun-like star. TESS wants to look at as many stars as it can, and it wants to look at lots of low-mass stars. So TESS actually has 4 cameras up in here. I should have pulled a slide of it, but I didn't. And basically, they're all pointed at opposite directions. So it's going to look at a huge patch of the sky, and it's going to shift itself. So it's going to try and look at as many fields as it can, and look for not planets that take a year to orbit, but planets that might take months or days, weeks, very short period planets. One thing I didn't talk about with TRAPPIST-1 is since all those planets are so close to their star, they orbit very quickly. I think that the shortest period one orbits on the time frame of days. Very short. So we're still in the gathering phase. We're trying to find as many exoplanets as we can. But then we're going to move to what we really care about. And that's biosignatures. For that, we need JWST. JWST is this billion-dollar telescope that NASA's been building forever that we're all worried is going to get funding cut at any moment. You know, we've been like building this thing for years and years and years, and at any moment somebody could say, no, we're not going to give you money, and then that's it. That's the end of this program. Luckily, I think we're past the point where that's going to happen, and this thing's going to fly. It's going to fly in a few years. I am showing you just the mirror portion of it here. So here's 2 guys looking at it in the clean room, and this is Hubble, just for comparison. And 2, I guess there's 3 guys, but I was trying to get 2. So you can see this thing is much bigger than Hubble. This is an engineering nightmare because you have to get this thing into space. And it takes a lot of effort to put something this big into space. But they figured it out, and hopefully it makes it up there. And it's going to be looking for something very specific. Biosignatures. This is what we care about. This is the ultimate answer to is there life in the universe? Unless people who are visiting some of the moons like Titan figure it out first. But we don't think there's any life necessarily in our universe. Maybe there's life outside of it, or in our solar system. Maybe there's life outside of it. So the way that they want to look for biosignatures is actually very interesting. You send a telescope up, and you take a spectrum So a spectrum just means you look at a star and you put the light through a prism. So a prism will divide it up, red, green, blue. But within the spectrum, you can actually tell the chemical composition of the star. It's imprinted in the spectrum. So if you get a spectrum of the star, when the planet is not transiting, the planet is not between you and the star, and then you get a spectrum when the planet is between you and the star, the planet, light from the star goes through the atmosphere of the planet. So the planet's atmosphere is imprinted on that second spectrum. It's somewhere mixed in with the star. But you have to get rid of the star. So if you take the second spectrum and you subtract off this first spectrum, which is just the star, you should get the spectrum of just the planet's atmosphere. And then you can see what's in it. What do we care about? We care about oxygen. We care about methane. We care about things that we believe life is important for, that life creates. You know, basically oxygen on this planet is due to all of the trees, the flora. So if you can find oxygen on a planet, that's a pretty good signature that there's some type of life there. Not necessarily intelligent life, but life. This measurement has been made, or attempted to be made, many times already. With Hubble, with Spitzer, lots of telescopes, ground-based telescopes. People have tried this tons and tons of times because the first person who finds it gets the credit. But we just don't have the ability yet. The signal is so weak, we just don't have what it takes yet. We need JWST. That's why we spent $1 billion on it. If I told you all it would cost you was $1 billion to find out if there was little aliens out there, you'd say that doesn't sound too bad. Now we can talk about a few complications with finding life on a planet around a low-mass star. This is a very busy plot, so I'll take my time and parse it out for you. The y-axis is energy output, and this is basically wavelength or color of light. So I have a few different stars plotted up here. The sun is in yellow. So you can see that the sun's peak output is around here. It's like 600-700 nanometers. Over here, at very small wavelengths, this would be like gamma rays, X-rays. And over here, this is the infrared. And then you'd have radio wavelengths way out here. But where the sun actually peaks, this is visible light. This is what you can actually see with your eyes. And then we have this F2V. This is a star slightly bigger than the sun. K2V is a star slightly smaller than the sun. And all of these things down here are low-mass stars. Some of you might not know this, but the fact that our sun puts out the majority of its energy in optical light is very important for the evolution on this planet. We see an optical light. It's not surprising since most of the light that we get here is from the sun. So we want to be sensitive to the wavelengths that the sun puts out the most. Also, photosynthesis. It works at these wavelengths. It doesn't work out here or over here. It's tuned to work with the sun because you want to be where you're going to be most efficient. So you want to go where the energy output is greatest. If I'm going to make a solar panel, I want to get these types of wavelengths. I don't really care about these types of wavelengths because the sun isn't really putting it out. But low-mass stars, they have very little output at these wavelengths. They're mostly in the infrared. So it's an interesting question about what evolution might look like on a low-mass star. Would these types of organisms see in the infrared, like the predator? I've used that reference so many times, I don't even know if it's relevant anymore. But we have no idea what this does to evolution, how important it is to evolution. It must be important to evolution because evolution and life require some sort of energy input. And almost all of the energy, at least on the surface, comes from the sun. This is where everything gets its energy from, except for extremophiles, which that's a whole nother lecture. One other complication is these stars tend to be very active. So what that means, here I'm showing you flare energy. So things higher up have more flare energy, and then this is flare frequency. So this point right here is saying that these very large energetic flares don't happen very frequently, which is good for this type of star. There's lots of different types of stars plotted here. I'm only going to talk about a few of these lines. This is the sun. This is active sun, and this is inactive sun. The sun goes on an 11-year cycle. So some point it's active, some point it's inactive. But if you compare that to typical M dwarfs, these red dwarfs, these low mass stars, you can see that on average, except for this line, but on average, these low mass stars have a lot of flares, a lot more flares than the sun, and at much higher energies. And that's bad. That's not good. Flares are very rough on life. You're just basically injecting these high energy particles into our atmosphere, and a lot of them make it down. So how resilient is life? Can life compete with this? Our magnetic field sheds out a lot of this stuff, but we don't know what magnetic fields of other planets are like. We don't know if they're stronger, they're weaker. That plays an important role in the ability for life to begin. The other thing you have to consider here is that these planets are orbiting much closer to the star. So not only are the flares more energetic, but the planets are getting a lot more of that energy because they're closer to the stars when these flares go off. That could be very bad. And the last point I'll leave you with, I don't have like a good plot for this, which is unfortunate, but this is the work that I did as a graduate student. But these stars, the planets around these stars have signatures that they might go through collisions. So I'm talking about something similar to the moon forming event. For those of you that don't know, we think the moon was created through a collision between our planet and a smaller fifth terrestrial planet that crashed into us very early on in the solar system's evolution. Luckily, we're bigger, and we won, so we got the moon, and it got kicked out. That's how the story goes. But there's evidence that planets around these low-mass stars might have these collisions frequently. And if I told you every billion years we're going to crash into Mars, that could be detrimental for life on Earth, because that's not good. It's like Armageddon times a million, basically. So we don't know if these planets around these low-mass stars can have life. But there's so many of them. There's so many of these low-mass stars, and there's so many planets potentially around them, that it's imperative that we still look for life, just because the numbers make it easier. You have a much better chance of finding life around a low-mass star. And that's like pretty good, right? Yeah.